equation that we're going to use. You don't have to title it. You can just write the equation. So very top of the back, let's write this down. Okay? What's that? No, you can use the full back. So we're going to just write this equation, and then we're going to have 4 different categories underneath it. They don't have a lot written in each category, but just so that you can space properly, because I know some of you care a lot about that. I'm going to use brackets in this case, but it doesn't have to be brackets. It could be whatever the function is. This would be a greatest integer function. Okay. Sorry. Okay. So basically, here is a function, okay? But we would see numbers where the A's, the B's, the H's, and the K are, and then I color-coded them for a reason. Notice that everything that is in here that's being applied to X. So stuff that immediately happens to X before you ever do whatever your function is. So it could be greatest integer function, could be absolute value, could be a quadratic, it could be a cubic, a square root. But this stuff right here that's inside the function is the stuff that happens to X before you ever do this special thing that you're trying to graph. All of the stuff that's in there, because it affects X, is going to cause horizontal changes to your graph. Okay? So basically, any numbers that are inside the function with X, anything I wrote up here in red, are going to be horizontal changes. Oops, except for that's blue. Okay? The stuff that is outside of the function, like the A that's in the front and the K that's behind, those things happen after you've done the special thing. So you've already rounded with the greatest integer, or you've already squared with the quadratic, or you've already taken the absolute value. It's like these things are affecting the y value of the parent function. They're changing the amount after you already did your special thing, okay, after you already got some output. So these things are causing vertical changes to our graph. Okay, so the first thing is we want to understand the numbers on the inside are going to do horizontal stuff. The numbers outside of the function are going to affect our graph vertically. Okay? Then we're going to look more specifically at what each of these things does, and I'll refer to them as the A, so that means the thing in this position, the B, the H, and the K. All right? Is this okay with everybody? All right, so the first thing we want to talk about is reflections. What causes your graph to reflect? So you saw it yesterday. Yeah, negatives. Okay, negatives in what positions? A and B. Okay, it's kind of weird. But remember when we did the greatest integer function, if there was a negative on the inside, the function kind of flipped over a different direction. Also, if there was a negative on the outside, there was a way that it flipped. So all the things that are causing these flips are going to be reflections. So basically, if A is negative, there's a certain kind of reflection, and if B is negative, there's a certain kind of reflection. So right underneath this, go ahead and write reflections. And then we're going to make 2 notes about what the horizontal ones are and what the vertical ones are. Okay. So if you have that A value, so I know this looks like weird notation, but f of x just means whatever your function is, right? So that greatest integer or whatever. You have the A outside of the thing with x, right? That's why the A is out here and not like nestled inside of here, okay? So this is saying the A is on the outside just like we wrote it in our example, okay? And basically, if A is less than 0, okay, basically meaning it's negative, we have a vertical reflection. Okay, think about what it means to be a vertical reflection. Okay, you saw this with your parabolas. What are they really getting flipped over on the graph? What's kind of like the mirror or the thing that you would fold over? Yeah, the x-axis. It's kind of weird. People confuse that because you guys think of the x-axis as a horizontal thing, and it is. But if I want something to change from above to below, what is it going to have to flip over on my graph? The x-axis, right? If it's going to go from up to down, it's got to flip over this horizontal thing right here acting as the mirror. So either people will refer to this as a vertical reflection or a reflection over the x-axis. And you can refer to it either way as well. Okay? But anything that's going from above to below or from up to down is vertical, and it would be because a negative is out here in front of the function in that A spot. Okay? Is this okay with everybody? Right, so if the A is not negative, but instead the B is negative, so that would look like this. Okay, again, I know the notation's weird, but I'm saying the number that's multiplying inside the function instead of outside. That means kind of where we put B in the little equation we wrote at the top. So if B is less than 0, or if B is negative, because it's inside and it's affecting x, which is horizontal stuff, in this case, we're going to have a horizontal reflection. Again, think about what horizontal reflection means. It means that something was on the left side of your graph, you want it to end up on the right side of your graph. Or if something was on the right side, you want it to end up on the left side. Okay? Good. So it would actually flip over the y-axis if you're flipping things horizontally, because you want something on one side, the left or the right, to end up on the other side, which means you've got to cross over the y-axis. Okay? So they would call this reflection over the y-axis. So is it okay with everybody that if you see a negative multiplying, you're going to think reflection? If it's on the outside of the function, you're going to think vertical, which means from up to down or over the x-axis. If it's on the inside with the x, you're going to think horizontal or like from left to right over the y-axis. Is this okay with everybody, kind of how to recognize a reflection when you look at the numbers in the equation? Okay. Yeah, Sean?
What's reflecting on the y-axis?
Uh-huh.
Just for purposes of doing like just saying that's reflecting over it?
For quadratics and absolute values, totally doesn't matter. So this is Sean's point. Let's say I draw a quadratic, right? And it flips over the y-axis. Does it even matter that it flipped over the y-axis? No. But let's say I'm graphing a step function and the step's only on this side and I flip that over the y-axis. Is it going to look different? Yes. So there are certain functions that, yeah, if you list it, it doesn't seem to have an impact on the graph, but in other functions it will. So we're learning one set of things that we can use for all different types of functions. That way we don't have to learn certain ones for each graph. Okay? All right. Are we good to move on from reflections? Okay. So next thing we're going to talk about are translations. So what is a translation? What is that doing on a graph? What is a translation on a graph? Okay, good. It moves over from where your original vertex point is. So left, right, up, down. So this is going to go below your reflections. So you wrote about reflections. Now you're going to write about translations. So what did we see yesterday in our investigation that causes translations? What caused our quadratics to move left and right or up and down? Which part of the equation? Okay, yeah, so inside parentheses. Okay. Which part of it, the B or the H? I kind of put him on the spot. So, all right. So the B it does the reflections and something else, but only the H is going to move things left and right on the inside, and only the K on the outside. So you know yesterday when your H and K values changed, those changed the X and Y coordinates of your vertex points because they were shifting your parabola either left and right or up or down. Okay. Yes. And they'll make up the vertex of all the functions that we start. That point that used to be at 0, 0 will now be at HK in every different shape. So that makes it really easy to remember. So first thing we want to look at, when we look at our K, if something's being added at the end of our function, okay, then it's going to shift our graph up or down depending on the K value. And again, I know the notation's weird, but I'm just saying you're adding the K like we did in our original equation. It's outside. It's after the brackets or the bars or the squaring or whatever was there. Okay? And then we have this idea, when that h shows up being added or subtracted from our x, then that's going to shift us left or right. Okay? So this red one, because it's shifting left or right, the one we wrote in red about h, this is considered a horizontal translation. Okay? And then the one that we wrote in blue, okay, the one that says plus k, because that's happening afterwards, that's where all of our vertical stuff was. This one would be categorized as a vertical translation. So when you're listing these and you see like a +4 at the end of your function and you know that that's in the k spot, you're going to say I have a vertical translation up 4 units. Okay? If you saw a -4, you would say I have a vertical translation down 4 units. Is that all right? Okay. So you guys are used to this. It's what you did yesterday on the investigation and with absolute value h and k. You just might not have called it a horizontal translation before, but you identified whether it was moving left and right or up and down. All right, the ones that are a little more difficult are the stretches and compressions. Okay. So the first one is the vertical stretch and compression, meaning you're taking the output and you're like multiplying it by something. So that a value, you guys saw this again yesterday in your investigation. When we put 3x squared, the parabola got a lot more narrow or skinny because it was like somebody took it and multiplied it times 3 and stretched it out vertically. Okay. So that a value that's in front of here is going to cause stretches and compressions, but you have to know whether it's a stretch or a compression. So you've got to look at the number part of A. So remember we said we kind of think about putting absolute value around it. All that means is we're not looking at the positive, negative part. Just look at the number part of it. Okay? And if the number part of it was more than 1, because 1 was the parent function, so 1's the basic shape. If you're multiplying by something more than 1, we saw that it was like it got stretched out when we multiplied by 3. It was like it got narrower. So this would be called a vertical stretch. And basically, I'm just going to make a little note here. You're going to take the normal distance you see in the parent function and you're going to multiply it by whatever that a value was. So normally, if I think things are 1 unit apart vertically, but my equation now has a 3 in front of it, I'm going to do like, okay, normally it's 1. Times by 3 would be 3. I now expect it to be 3 apart instead of 1 apart. And that's going to let you stretch the graph out. Okay, and we'll do examples of that, so we'll be okay. The other option is if the numerical part of the a value is smaller than 1. So I'm not talking negatives here. I'm talking like 1/2, 2/3, things that are less than 1. Okay. So you guys saw with 1/2, it looked like someone made your graph wider, like they squished it like this. So that was a vertical compression. And the way you would do that is still the same way. You're still going to multiply stuff by whatever that a is. So if my point used to be 1 apart in the parent function, but somebody puts a 1/2 there, I go, oh, it's normally 1 unit apart. But there's a 1/2 there. 1 times 1/2 is a half. I'll only draw it half a unit apart, and that will compress it lower because the number's smaller than 1. Okay? And again, we'll do examples of exactly how to do this so that you'll see. Is everybody okay with vertical stretches and compressions? So you look at the number out here, you literally use that number, and if that number's bigger than 1, you're timesing by something bigger than 1, so you're stretching stuff. If it's smaller than 1, when you times things by something smaller than 1, they get smaller, so that's why it's a compression. Okay? So the horizontal stuff gets a little bit, oh, yeah, this shouldn't be here. That's nice. So the horizontal stuff gets a little bit trickier. So remember, all the horizontal stuff is on the inside. Okay. So this time, rather than looking at the a, the number multiplying outside the function that's happening when everything is done, we're looking inside the function. There's some number that was multiplying our x. So we're looking at that b value. Okay. You guys saw this in your greatest integer function. So think about your greatest integer function. When you saw a 2 inside of the brackets versus a 2 outside of the brackets. Okay. So the 2 outside of the brackets is like the last thing we talked about. It's vertical, right? It's not inside the function with x. It's outside. So it's an A value, which means things got multiplied by 2. That's why your steps got further apart vertically. They were 2 units apart instead of 1. Okay? So that's the vertical one. This is the horizontal one because the 2 is inside the brackets with X. Now, what happened to your steps when we put a 2 in there? They were normally 1 unit long. When I put a 2 in here, how long are you going to draw your steps on your graph? No. 1/2. Remember, all the horizontal stuff was weird, right? Instead of multiplying it by 2, it got multiplied by the reciprocal of 2. So instead of being a unit long, our steps were only half a unit long. Okay? So that's the part that's going to be weird about the horizontal stretches and compressions, is that instead of just taking this number as it is, we saw that that's not really what happens. We really use the reciprocal of that number. Okay? So that means when b is bigger than 1, so when b is a number like 2 or 3 or 4, are your things getting longer or are they actually getting shorter? They're getting shorter, right? We put a 2 in here. Our step didn't get longer. Our step got half as long as it used to be. Okay? So when the number's bigger than 1, this works the total opposite way that we would think. This is not a horizontal stretch. This is actually a horizontal compression. So the best way that I can think to help you guys with figuring that out is to memorize that you're not going to multiply by 2. What are you actually going to multiply by when this says 2? The reciprocal, 1/2. So basically in these problems, everything's getting multiplied by the reciprocal, okay? Which means when you had a big number, once you flip that big number over, it's actually a really small number. So once you look at what you're multiplying by, that will tell you whether it's a compression or a stretch, okay? Because the number will be 2, so you'll think, oh, it's big. But then when you see that you're multiplying by 1/2, that should give you a hint like, oh, I'm actually making things smaller when I multiply by 1/2. So I'm going to call this a horizontal compression. Whereas when the number is smaller than 1, okay, so think about it this way in your head. If you had a 1/2 inside the brackets with x, how long would the steps actually be in this function? 2, right? So again, think about what you're multiplying by, the reciprocal. When you see that the reciprocal is actually multiplying by 2, that will help you label it correctly and say, this is actually a horizontal stretch because I'm multiplying by this bigger number. So my advice would be to memorize that with the horizontal stuff, you need to use the reciprocal, and with the vertical stuff, you don't. But for both of them, once you know what you're multiplying by, if the number's big, it's a stretch. If it's small, it's a compression, right? But after you've looked at what you're actually multiplying by, okay, which here means the reciprocal. And again, we'll do examples of that. So these are all of our transformations. Okay, so when you look at an equation, you have to be able to name any reflections, any translations, any stretches, and compressions. Does that make sense to everybody, kind of the category of things that you're looking for? Right? Okay, so on the front side of it, we're going to use the doors to put our parent functions because we have to have those memorized if we're going to stretch them and compress them and reflect them. We have to know where the points are for those. And then we're going to go through an example of each kind so you guys can just see how the process works. Okay? So on the first door of your organizer, so we'll go ahead and put the absolute value function right here. We're going to end up doing the greatest integer right here and the quadratic right here. Okay? So we're going to review 2 that we've already done and do the quadratic one as our new one for today. Okay? All right, I have like 4 graphs. You guys don't need 4 graphs, but I wanted to take you through each of them individually. The first thing I want you to write on the front side of the absolute value door is the name, absolute value, okay, or absolute value function. And then I want you to put the parent function on the front of the door, okay? So remember what the parent function looks like. For the absolute value, it had a vertex at 0, 0. Okay? And then basically the lines went up in a V with a slope of 1. So in that direction with a slope of 1 and in this direction. Just draw an XY axis and make a little sketch of it. Okay, so that is our parent function. So on the front of the door, you just have the name and the parent function. Okay? Is that good with everybody? In the graph, yeah. Oh, yeah, and the equation of it. Thanks, John. That part would be important. So what I have up here so far, the name, the equation in the little graph right here is on the front of your door for the absolute value function. Okay? So if you forget, oh, what does absolute value function look like? What's the parent function? Where are the points? You have this reference with all your parent functions in one place. Okay? All right, then go ahead and open up the door. Okay? And you should have 2 spaces to write, right? Each side, like behind the open, like the back side of the door, and then the open space that you got to. So what we're going to do there is we're going to graph an equation on one side. You're not going to do all the steps. You're just going to write the final outcome. And on the other side, we're going to write down the transformations for the equation. Okay? So on one of your sides, go ahead and write down this equation. So -2, the absolute value of x plus 1 minus 4. So first thing I want to do is, can we identify the transformations? So what are the transformations here? So, Ramsel. Okay, good. So we're going to call it a vertical reflection. So underneath the equation, let's just write down the transformations, right? Because of this negative out here, there is a vertical reflection. What is the 2 causing? So first of all, is the 2 vertical or horizontal change? Vertical, because it's outside of the absolute value bars. Okay? And so the number in the A spot, remember, is either causing a stretch or a compression. So when it's vertical, do you get to use the number that's there, or do you have to flip it over and use its reciprocal? Use the one that's there. All the vertical stuff is easy. What you see is what you get. All right? Like how H is difficult but K is not, that kind of idea. So this says 2. So I'm literally going to be multiplying stuff by 2. Okay. Multiplying stuff by 2, does that make it bigger or smaller? Bigger. So this is a vertical because it's on the outside. Because multiplying by 2 makes things bigger, will I be stretching them or compressing them? Stretching them, okay? What is the plus 1 inside of the absolute value going to do? Okay, it's going to move it 1 unit to the left. And what kind of transformation is it? A horizontal translation. So you guys can actually list your translations together if you want. If you just want to, you can write translations, and then you can say 1 unit left. And what's the other translation that we have here due to the minus 4? 4 down. Okay? So you guys have graphed absolute value function before, so you understand how these work. I just want to change your perspective a little bit. Let's say I just did the translations, okay? I know that that's going to change the vertex from being at 0, 0 to being at -1, -4. Is that okay with everybody? Because of these translations right here. So -1, -4. If nothing else changed, then the graph would still look like this. You guys don't write this graph down yet. Don't write it down till the end, okay? But are the translations the only transformation that we have here? No, okay? What is the vertical reflection going to do to our graph? Yeah, it's a flip over the x-axis. So here's what I have to ask you guys. If you're going to literally flip it over the x-axis, you need to do it before you move it. Because if we flip it over the x-axis now, the vertex is going to end up in the wrong place, right? So you either have to do your reflection first, or since I've already moved it, instead of really reflecting over the x-axis, you can use your vertex point for kind of your reference for everything. I can just flip it over the vertex point, right? Keep the vertex point in the right spot according to H and K, and then do everything around the vertex, okay? So if I do the reflection, I keep my vertex at -1, -4, but now it looks like this. What have I still not accounted for, though? The vertical stretch. So here's what I want you to understand about those stretches. They're taking a distance that used to exist, a vertical distance that used to exist in your parent function, from the vertex to whatever other point that you graphed. So, for example, this point right here. How far is that point vertically? I only care about vertical stuff because I'm only doing a vertical stretch right now. That point is how far vertically from the vertex point of the graph. 1 unit, right? I am literally going to take that number, okay, the measurement from the parent function, and multiply it by whatever my stretch or compression number is. So 1 times 2 is 2. That means I want to redo this graph, vertex in the same place, but the point that used to be 1 unit away from the vertex vertically, I now want it to be 2 units away from the vertex vertically. Am I changing how far it is left and right from the vertex? No, because that's horizontal stuff. So if I'm looking at this point, it was go 1 over and then go 1 down. I'm still going to go 1 over, but rather than going 1 down to draw that point, I'm going to go 2 down because I want the new distance from the vertex to be 2 units. Okay, that's how the graph is getting stretched. So this point would end up being here. Okay? Same thing for the other point. This one was also 1 unit away vertically, right here. So it would be 2 units away vertically here, and then that would be my new graph. Okay? So go ahead and draw the graph in now. So this is the final graph. This is what you want to draw. Give yourself an x and y axis. The vertex would be at -1, -4. And rather than the points being 1 away and only 1 down, they're going to be 1 away horizontally and 2 down because of our vertical stretch, and downward because of our reflection. Oops. You guys wrote this yesterday on your cosmic catalog. So the parent function was just x squared. So this is on the front of your quadratic door. It had a vertex at 0, 0. And the points were 1 away and 1 up, and then 2 away and 4 up. And again, how did I know that so fast? I told you guys yesterday, this is a key piece of information we would want memorized so that we are able to know what the parent function looks like from the beginning. So on the front of your door, the parent function. So name quadratic equation y equals x squared. Quick sketch of this graph. Function. Then open up your door and write down this equation. So y equals 2 times x minus 1 squared plus 3. And then we're going to list all the transformations. So there are no reflections. Because of this 2 out here, there is a vertical stretch or compression. Remember, with the vertical stuff, you take it as it is. So I'm going to be timesing stuff by 2, which is going to make them bigger, which means it is a vertical stretch. The only other things I have in my equation are translations. And the translations here, the h is positive 1, so we're going to go 1 to the right. And the k is positive 3, so we'll go 3 up. Now, I don't want you guys to write the graph again till the very end. But know that we can go to our vertex with our translations, right? So 1 to the right and 3 up is going to be my new vertex. And if there were no other changes, from this vertex, I would follow the same pattern. Over 1, up 1, over 2, up 4. And that would be my parabola. But there is another change. What's the other change that I haven't done yet? The stretch, okay? What are we stretching from? What are we measuring things from and saying, oh, I'm going to make their distance bigger? The vertex, okay? The vertex. So this guy's going to stay at 1, 3. But these points around it, I'm going to change their vertical distance because I'm just doing a vertical stretch. So normally from the vertex, excuse me, when I went 1 over, I would go 1 up. Okay? But that distance right now is going to get stretched by a factor of 2. So I'm going to take the 1, I'm going to times it by 2. 1 times 2 is 2. So now when I go 1 over, I don't want to be 1 above the vertex. I want to go 1 over and be 2 above the vertex point. And same thing on the other side because it was the same distance. Okay. Now, when you go 2 over in the parabola, how many points above the vertex do you normally go? 4. So the normal structure is that this is a distance of 4. If I take that and multiply it by 2, what do I want my new distance to be? 8. Okay, so I'm not going to really be able to graph the points on here. But if I went 2 over, I want to be 3, 6, 7, 8. 8 above. Okay, instead of 4 above. So notice that when it's a vertical stretch, I'm taking the points around the vertex. I'm keeping the vertex in the same spot. I'm taking their old measurement, multiplying it by something to give me a new number, which is how far apart I want them to be from the vertex spot. Does that make sense to everybody? Okay. Now, the only extra thing you would see on the homework tonight is possibly a vertical reflection, which means this whole thing would exist except for, again, the vertex would stay in the same place, but the points, instead of being above the vertex, would be below the vertex. Okay? So go ahead and draw your final function in there so you have it for reference.
So we're doing